And we are now recording. Let's go. Well, I thought it was set up here. I'm not. From the current slide. Okay. Before we get going with that, two announcements. First one, pretty important. Okay? I'll give you a little bit of background first. I don't know if you all are familiar with SACS, the Southern Association of Colleges and Schools, Commission on Colleges. They're the people who accredit us and all the schools in the Southeast. Okay? And we are having a SACS reaccreditation visit coming up in the next few years. I don't know, it's not super far away, but it's close enough that we are beginning to prepare for it now. Okay? Now, why am I telling you that? You're not going to be here then, right? But they look at past history. They will be looking at what's happening now. And one of the things they really pay attention to, or it sounds like they do, is the student course evaluations. Y'all done them yet? Yes. Not yet. No? Okay. You know how to do them? No. Okay. How did you do them? Did you get the email or did you?
Yeah, I just got the email.
And you clicked on the, okay. Do you check your lost and email at all? Okay. Do you even know how to check your lost and email? Probably not. Huh?
Yeah.
You do? Okay. If you do, go to your lost and email. And how long ago was it? Probably a month or two that they just did it, but it was back there for a ways, wasn't it? Okay. So if you go to Lost State email and check the one, was it entitled something about evaluations or something like that, course evaluations, look for a title like that in your email. And if you find it, click on it. There'll be a link. Click on that. You go to it and do it. What did it take? 5 minutes or less? About 5 minutes. It does not long, and we get really good information from it. Not just me about the course. I get information from y'all, just about every time we meet. But also you'll be asked to do maybe one or two other evaluations of other things, like the registration procedure, the library services, or something like that. Grounds or whatever, building maintenance, I don't know, whatever. Whatever. But you might get one or two other evaluations to do. Please do those as well. Like I said, feel like I get interaction with you every time we meet. Those folks don't always get the interaction from you, so they really need that information. But I treasure the information you give me too. I want to become a better instructor. So please do the student course evaluations. We have sort of gotten slack on them. Seems like our percentages have gone to something like less than 50% participation. They're wanting 80% participation at least. So please do the student course evaluation. All right, so that's the one. Please do that. You can do it up to final exams. I think they even leave it open a couple days after that. If you wanted to see what your final grade was before you do it, that's okay. But they really prefer to get them in sooner so they can, before y'all get away, then they have no way of getting in touch with you to say, hey, are you going to do your student course evaluation? So try to do them sooner rather than later. Okay, that's one. The second one is not nearly as important, I'm guessing, for y'all, but or for the school, but I just wanted to let you know. Normally I have office hours on Fridays, 7:45 to 11:45 on the Birmingham campus. Not this Friday. I've got a treatment coming up, an infusion on Friday, and that basically I'm there usually from well before 7. I don't know what time my infusion is this time, but usually I'm there before 7 and don't get home until, say, around 4-ish or so. So I'll be there all day. And then even when I get away from there, I'm not going to drive too far. So I'm going to drive straight home and usually go to bed. So because they give me Benadryl and stuff, and that kind of knocks me out. So I won't be going back to campus after that's over with. Anyway. All right. Any questions before we get going on today? All right. From my memory and Mark in the book, we're in Chapter 14, Differentiation in Several Variables, Section 14.5. the gradient and directional derivatives. And example 4, goodness, I'm stiff and sore from the busy weekend. Oh, man. Example 4, the temperature at a location, xy, is T of xy. And that temperature, let's see, this is yeah, okay. I couldn't remember that they had given us the definition of the gradient, but they have. So just showing you before I write down what it is, this is the temperature distribution, and it's a three-dimensional graph done in 2 dimensions, okay? Temperature, no, I'm sorry, it's in 2 dimensions, okay? Temperature at any location xy is T of xy is equal to 20. Okay, so this isn't shown on here. The temperature isn't. This is just the xy plane, okay? But the, I'm going to have to shrink it so I can write on it, okay? Here is the temperature distribution function, you might say. That temperature, if I can get my pen activated in the right color here, T as a function of x and y is equal to 20, goodness gracious, 20 plus 10 e to the minus 0.3 times x squared plus y squared. Okay? And that's given in degrees Celsius. It's a temperature function, so that's what it would be. Now, just to give you a little bit of feel for this, at the origin, 0, 0, this will, of course, be 0. E to the 0 is 1, right? And this would be 20 plus 10, that would be 30 degrees. At the origin is 30 degrees. Okay. Now, anywhere beyond that, let's just say x equal 1, y is equal to 0. So we'll go over here to 1, 0. Okay? Now, that would then 1 squared would be 0 squared is 0. That would be 1 times 0.3. That would be 0.3. So e to the minus 0.3 is going to be a number less than 1, right? So that's going to be a smaller number here times 10. Still going to be something added to 20, but it's not going to be as much as 10. So the temperature, boy, this is hard to see on this. But the temperature is increasing going toward the origin. No matter what values you put in here, other than 0, 0, this thing will always be something less than 1. So something less than 1, you're multiplying by 10, that'll be something less than 10, and adding that to 20. So everything, the maximum is at 30 degrees at the center, and everything else is less than that, and the temperature is increasing as you go toward the center. And that's what this is showing here, okay? And it's pretty much a radial distribution, because whatever your x and y are is coming in toward the center. So that's pretty much a radial distribution. Okay. All right, so there's your temperature function. This book can really get cutesy sometime. A bug carries a tiny thermometer along this path, and here is the path. Now, in the old text, they call this C. this is going back to R, which I prefer. R, okay? It's a vector function. Here's the path he's taken. R of t is equal to cosine, and here's another improvement in it. Since this is a vector, they put it in vector notation, okay? The x component of the vector is cosine of t minus 2, and then the y component is sine 2t, okay? So that's the path along which this bug travels. And that's what the green is, just sort of meandering about there smartly, okay? Okay. And t is measured in seconds, and that is the figure for it there, okay? How fast is the temperature changing at t equal 0.6? So we want to know how fast t changing at, now this isn't temperature, is time. T is equal to 0.06 C is equal to 0.6 seconds. Okay. Now, what you need to know here, number one, is where on the path is the bug. Okay? And this is saying C prime. That should be an R prime now, the way we're doing things now. That would be the point R of 0.6. Okay? That's the point. Now that point is not a vector, so that's not quite a great representation of it, but you know, the R at 0.6, T is equal to 0.6, which is what we're doing. That's where the bug is, and he's moving in that direction because the velocity vector is in that direction. Okay. So, how is the temperature changing there? Well, the first thing they do is calculate, like I said, where the bug is there. So you do your R of 0.6 seconds, okay? And that will be the vector cosine of 0.6 minus 2 would be 0.6 minus 2, t minus 2. Negative 1.4 seconds. I'll leave off the units now. Okay, comma, sine of 2 times 0.6. And what's that? 1.2. And that would also be seconds, but I'll leave off the units for it. So there is the location of the bug at that time. Okay? If you got a calculator, be sure you're in what mode? Radian mode. Just about always in calculus. A lot of time in physics, you're going to be in radian mode. So that's going to be, give me approximate the values there. Cosine of negative 1.4. And just for funsies, let's think about this for a moment. Where are you when, okay, t is negative 1.4, okay? Cosine is what kind of function, even or odd? Cosine, even or odd function? That means, huh? No, it's even. Remember how a cosine function looks? It starts at 1, and then it goes down like this. That's even. It reflects across the y-axis. Oh, okay. Right. Because cosine of negative x is the same as cosine of positive x. Yeah. Wherever they are, they're the same values, as long as you're the same distance from the other thing. So this is going to be the same as cosine of positive 1.4. Yeah. Because it's an even function. 1.4, if you think about this, this is 0, that's pi halves. Well, pi halves is about 1.5, isn't it? Because 1.57 or something like that. Because pi is 3.14. Half of pi is 1.57. Okay? So this is something less than that. So you're in the first quadrant. I mean, you're in the fourth quadrant there, but the cosine is positive, so that's going to be a positive value there. And the sine of 1.2, again, that's in the first quadrant, that's positive. So we've got your position is in the first quadrant, positive x, positive 1, okay? Positive x, positive 1, okay? So, if you will, punch in the number. I just did that so you would get an idea of what to look for. What is cosine of negative 1.4? Say again? 0.16, 0.16 approximately. And sine of 1.2? 0.93. Okay. 1.2 is getting fairly close to 1.57, which would be pi halves, which would be 1. So yeah, those sound like very reasonable numbers. 1.4 is getting close to where cosine of pi halves would be 0, so you're getting close to 0. So that does sound reasonable. Okay. They did 1.70, I mean 0.170, they said, and 0.932. 169? Okay, and what's the next digit after that? 169. Cosine of negative. 99. So that's awfully close to 0.17. So let's make that 0.17. Now we're not rounding as far as they are, but yeah, we got the general idea. So there's the point where you are. Okay. Now that's where you are. What is the temperature doing then? How is the temperature changing there? Well, to have a change of temperature, that's kind of like a derivative, right? But you're in 2 dimensions. So how do you do a derivative in 2 dimensions? Well, that is your gradient function. So what you've got to do here is do the gradient of t. Do you remember how to do that? Gradient is a vector. So start it out with a vector notation. Okay? And the x component of your gradient is going to be the partial of t with respect to x, and your y component of the gradient is your partial of t with respect to y. And if you turn back one page, you'll see that at the top of page 775. Okay, yeah, you're using a different book, that's right. Okay, so let's take the partial of this with respect to x. What's the partial of 20? 0, yeah, nothing there, okay? So we're only going to do the partial of this with respect to x. Well, what would that be? You go and give it out in gory detail. It would be 10 e to the minus 0.3 x squared plus y squared. You remember a derivative of an exponential function is an exponential function. But then you do a chain rule on it with respect to x would be with respect to x would be negative 0.6x, right? Okay, you see that? Okay, so if you're doing a negative 0.6 by 10, that would be 6, right? So that would be negative 6. I don't think I'll put a 0.0x e to that. That's going to be the gradient in the x direction. the component of the gradient in the x direction, and the one for the y direction basically is going to be identical to it, isn't it? Only it's going to be a 2y in front, right? Because the partial of this with respect to y is the same as it was with respect to x, except you got a y in there. So this is minus 6y e to the minus 0.3 times x squared plus y squared. Okay. Now, that's how much the temperature is changing in the plane, in that plane, at any point in the plane. Well, we want this point, when x is equal to this and y is equal to that. So all we do is plug in that for x and that for y. So if that's where you are, and that will give you your gradient there. Okay? So, well, one, not quite adequate is the beginning of it. But you want this, because they really didn't say, they said, how fast is the temperature changing at t is equal to 6/10 of a second? Well, that's changing with respect to time, because they're giving you a time, so it's changing with respect to time. So we're interested in dt, and that's that's not a vector itself. T isn't. As temperature is not a vector quantity. dt. Capital T is temperature, lowercase t is time. That's what we're looking for. Okay? Now, if you flip back one page, or just look on the other side of the page, you see the chain rule for paths. Okay? And we're doing d by dt, t of some other function of t. And this would be of xy. Okay? And that would then be, your definition there would be the gradient of t, okay, times the, is sort of the chain rule, that's what they call it, the chain rule for functions, okay, chain rules for paths, let's say, okay. So this is the gradient function. Remember, that is a vector, so I like to put the t function is not a vector, it's a scalar function of temperature, but when you take the gradient of it, it'll give you a function, and you dot that, remember dot products, with your r prime, okay? It's not r itself, but and that's why they showed this here. You dot it there, and that gives you how fast the temperature is changing with time, okay? Because the bug is moving this way, and it does look like the temperature may be decreasing because you're getting further from the origin, decreasing, so I would expect that to be a slightly negative quantity. Well, let's see, we still got to do r prime. We've got our gradient. What is your r prime? We hadn't done that. R prime of t would be what? Also a vector, okay? Derivative of cosine. Okay. Okay, wait, yeah, you do this one, not this one. That is a certain value. What would that be? You said negative?
Would it be positive then?
Second?
It's negative sign.
Yeah, but derivative of cosine is minus sine of t minus 2, right? Comma.
Negative cosine.
Cosine of 2t, and chain rule then would give you, I'm sorry, a 2, right? Okay. All right, there's your r prime vector. Okay, now we're going to evaluate this at 6/10 of a second. So r prime at 0.6 seconds is going to be negative the sine of how much?
Negative 6 y.
Negative what?
Negative 6. Or I mean,
The t is 0.6. 0.6 minus 2 would be negative, same as we did before.
okay,
The t is 0.6. That's what t is. Plug in a 0.6. 0.6 minus 2 is? Second? 1.4. 6 and 4 is 10, right? Okay. But it's a negative 1.4, just like we did down here. It's the same argument there, comma, and this will be 2 times the cosine. It's a pretty ugly cosine. 2 times 0.6, which is? Say again? 2 times 0.6? 1.2, exactly. Okay. Now, when we plug that in, sine is an odd function. So sine of negative 1.4 would be the minus the sine of 1.4. But then you're going to negate that again, so that can be the sine of 1.4. Wait. Yeah. No. Yeah. And basically, that's going to be some positive number. Not hugely positive, but somewhat positive. So in the x direction, this does have a positive component. And this one, cosine of 1.2, you're still in the first quadrant, so that's a positive number. Multiply it by 2, and you get a fairly good cosine. So your x component is positive, your y component is positive. That's over your velocity vector. Okay? That's your velocity vector right there. So sure enough, this looks reasonable. So what we're going to do is dot those two. We've already done this function. That's 0.17, 0.93. Oops. Dot that with, and we'll need to figure out what those values are. The negative sine of negative 1.4. Negative sine of negative 1.4. I would just do the sine of negative 1.4 and negate it, but whatever. What does that give you? Second? Yeah, the sine of negative 1.4. Okay, again, 0.985. And that makes sort of sense because that's a bigger number than the sine was before. So that was 0.93. Okay, next. 2 times the cosine of 1.2. 0.725. Okay, so there is your r prime at that value, t equal 0.6. Okay, now what you do is something fishy here. Oh, no, I wrote down the wrong thing. Didn't I? Yeah, sorry about that. No. Sorry. No. I said that the gradient at that point. Okay. Sorry about that. You have to now calculate what the gradient is at that point. Okay. So there was your value. Right, my knees are stiff. Here's the gradient. Okay. Now, your x value is 0.17, and your y value is 0.93 of your r. Okay, that's what goes here. So this is going to be just a tad on the messy side, so let me go on and write it out a little more clearly. This will be the gradient of minus 6 times 1.17 e to the minus 0.3 times 0.17 squared plus 0.93 squared. Okay, that's the x component, comma, minus 6 times y, which is 0.93, e to the negative 0.3 okay. Oh, I was trying to figure out what that symbol was. I see it now. And this is also 0.17 squared plus 0.93 squared. Okay. When I was looking at this, I said,
Okay. Oh, never mind. I see it.
yeah. Well, look at this. This doesn't make any sense. I was thinking it's e to a negative 0.3 times 0.17 squared. I said, why in my parentheses there? That's not a parenthesis. That's the comma from the previous step. So that's not a parenthesis there. That's the comma from up here. So basically, it's this number, this and that. To save yourself a little grief, go on and do 0.17 squared plus 0.93 squared, and multiply that by negative 0.3, okay? Whatever number that is, that's what you're going to take the e off, so go and take the exponential of that number. And then you can multiply it by minus 6, whatever that value is, and then multiply that on this side by 0.17, that side by 0.93. So what do you get that gradient to be? According to the graph here, it looks like you have a slightly negative x and a fairly negative y. Okay? And that looks reasonable with the numbers here, but I'll let you decide, because 0.6 times 0.17, 0.17 is awfully close to 1/6, right? So that would be almost a negative 1 times a number that's a fairly small exponential. I think it is anyway. So that's going to be a slightly negative x value, okay? And then the other one, though, is going to be something that is a good deal larger, but still negative y value. So what do you get these components to do? When you plug this in, remember that's not a parenthesis. Get it out of there just so it won't be confusing. And let me put it back where it belongs. Up here. Okay, that's the comma that separates the two.
You might want to check this from the book, but I got for the x is negative 0.78.
That sounds pretty reasonable. You get it to negative 0.78? 78, is that what you said?
Yeah.
0.78. And what's the y value? I would guess that's, what's that?
I got a negative point. I'm going to feel around it to negative 7.30.
Okay, 7 point. negative 7.3. Is that what you said?
Well, it's negative 7.2960.
Yeah, let's just call it that. Okay? Now, let's see. I don't know if they did that, showed that in the book. They didn't show the evaluation. Oh, there it is. There it is. Negative 0.78. That's what they got. Whoa, no. They got a negative 4.3 or something like that, not 7.3. I thought that was a bit much because.
So it's 0.93.
Say again?
I'm trying to make sure I'm reading right.
Okay.
So it's negative 6 times 0.93.
93 times e to the negative 0.3 times, now be sure you put that in parentheses, 0.17 squared plus 0.93 squared. Because I'm pretty sure that the
You said negative 0.43. Is what they had?
negative 4.3. Okay, right. Okay, yeah. Okay. Negative 4.3. So when you do those, that was negative 4.3. I'm not taking as many digits as they are. Negative 4.3. Okay. Now, when you do the dot product of these two, this will be a negative 0.78 times a negative 0.985. Okay. Plus, which in this case actually going to wind up being a minus negative 4.3 times 0.725. And when you do that, that will give you the rate at which the temperature is changing with respect to time at that point. How fast is the temperature changing at that time? So if you got a calculator, do that. Negative 0.78 times 0.985 plus negative 0.43 times 0.725. See what you get. Say again?
No, I missed a little bit. Was it 985?
0.985. 0.78 times 0.985 plus
That's 225, right?
225.
No, that's not the answer.
Oh.
I was saying right on the board.
Okay. Oh, this one here, that's a 725. I think. Usually I slash my sevens and that looks more like a 7. There's a 2, so that's a 7. So it's this product plus that product. This is falling apart. Shoulder aches, everything aches.
Probably want to check this one, but I got negative 4.85.
They got negative 3.97. Let me just see. Oops. Nope. Okay. So let's try it one more time. Negative 0.78 times 0.985.
What? 0.985?
Yeah. Plus negative 4.3 times 0.725. No, 0.725.
Yeah, I got negative 3.88. Well, 3.89.
Okay, they got negative 3.87, which is close enough. Negative 3.87 degrees per second. okay? It's degrees Celsius per second, okay? Now, and like I said, as you're moving up the curve here, you see you're getting slightly cooler because it's warmest toward the center and you're dropping as you go up. And since you're moving in that direction, you're moving away from the origin. So it should be a slight change in, a negative change in temperature per second as you go. That's not a lot of change, but it was actually a little more than I was expecting because you're moving away, but I didn't think you were moving away that rapidly. Let's see. I left off the notation there. It's R prime there, not R. Yeah, I left off the R prime. No, I didn't. Sorry, I'm sorry. You know, no. This was right. Okay, sorry about this. Okay. I didn't write down over here what this was. I wrote it here. This is that one. This is that one. Okay. So, take out one of those. Okay. I thought I'd written it somewhere else, but I hadn't. I just wrote it down there. That's the gradient of the temperature at this value. That's what you plug in for the X and Y, but you dot that with R prime, which is these values which you plug in at time 0.6 seconds, okay? So that's how you came up with those two numbers, and then when you dotted those together, the product of these two plus the product of those two, add those together and you get this. Okay, good deal. All right, any questions on that? Now, in the next example, we also apply the chain rule for paths to a function of 3 variables, okay? So we can do it the same way we did before, just I don't think we're going to have a slide for this because it's sort of hard to draw it 3 dimensions. So let's just clear all the ink from here. Have you got this okay? All right. We don't have a figure for this, but just to remind ourselves what the chain rule for differentiation in 3 variables is. So you've got d by dt of some function f of x, y, and z, okay? And this is going to be the gradient of f, which is a vector, dotted with the, okay, and this is your r of t, okay? Dot that with the r prime of t, okay? The x, y, z is that r of t. That's your position vector. Now, so what we've got to do on this one is calculate d by dt of f of r of t okay, when t is equal to pi half. Okay. Where f of x, y, z is x squared plus, xy plus z squared. I can't read. Where your f of x, y, z is equal to x, y plus z squared. Okay. Now that's the function that we're taking the gradient of, okay? And that's not x to the y of. For some reason I wrote the y too high. And this is not the figure for it. So don't get that confused, okay? So what let's see. And your position function r of t is equal to cosine t sine t t. Cosine t sine t t. Now, does anyone remember what that is? Do you recall? We've dealt with them a few times before. Okay. Cosine t sine t, if you just add that, that's going to be a circle. Okay. Now, if the y is going increasing with t, and the xy plane, let's have the floor being the xy plane, and there's the z plane upward. Your z is going with t. This would be a circle that's going like this because it's called a helix, a spring-looking thing. Circular cross-section everywhere, and you're increasing with t going up the z-axis. Okay? So there's your r. Okay? And we're going to be figuring this when t is equal to 1/2. So one thing you're going to do is figure out what r at 1/2 is to find out where you are. So, say 1/2, pi halves. I can't read myself. Yeah, pi halves. So what is r of pi halves?
That would be
0.
0,
1.
pi.
Pi halves. Yeah, exactly. Okay. What else do you need to do?
I don't know.
Yeah, it's right up here. You need two more things. You need the gradient of f, and what's that? Gradient of f. Now, f is a scalar function, but when you take the gradient of it, that gives you a vector function, and what would that be?
With respect to x, right? Like partial derivatives?
Yeah, you do a partial derivative. The x component is with respect to x, the y component with respect to y, and the z component with respect to z.
Okay.
Yeah.
And it'll just be y.
Y, comma,
Yeah, y, comma,
x, comma,
and then 2z.
2z. You got it. There's your gradient of f. Okay? Now, you're going to evaluate that at the place where y is equal to this, where x is equal to that, and where z is equal to that, because that's your position vector. So this gradient of f at that point, t equal pi halves, is now going to be, the y value is 1, the x value is 0, and twice the z value would be pi. Okay, got it. All right? So there's the gradient at that point. Now we also need r prime. So r prime of t is what? Negative sine of t, cosine t, 1. Okay? Now we plug in what our t's are there too. So r prime of pi halves will be
I have to
negative 1, comma, 0, comma, 1. Got it. Okay? All right. Okay, so we're going to dot this r prime at t is equal to pi halves with the the gradient of f there with r prime there, which will be dotted with negative 1, 0, 1. And what does that give you? This is d by dt of f of r of t. What's the dot product give you there? Negative 1.
0.
Yep. Well, it's not a vector. You're adding them up. Negative 1 plus 0. Remember, a dot product, the scalar product, you do this product plus that product plus that product. You're adding the products together.
Yeah. Oh, plus.
Okay, I'll write plus 0. I just did.
Oh,
Okay.
and then plus pi.
Plus pi, which I think I would write as pi minus 1, which would be 2.141. Okay, let's see what they got. Pi minus 1. That's exactly what they got. Good for them. I'm proud of them. Okay. Now, we're going to approach a new subject here. We got gradients down now fairly well, right? And chain rule for gradients along a path, chain rule for paths, okay? Now we're going to start talking about something called a directional derivative, okay? And I guess to get a better feel for this, I don't know if this will give it to you, some warm and fuzzies, but okay. Now, the directional derivative, and we use the nomenclature, the way to express this. Derivative is the capital D. The directional derivative means the derivative in the direction of the u vector. So that's your direction, is in the u vector. Now that u vector doesn't have to be a scalar. I mean a unit vector, I don't think. Okay? I think it can be any vector in the direction u. Of a function, alpha AB, now we're going to start in 2 dimensions, later we'll move to 3. Oh, yeah. Will be the derivative in the direction of u of the function AB is the rate of change of f along the linear path through the point P, which is AB, that is the point P, AB, within the direction of the vector u, whatever that u happens to be. Okay? Now, again, to conform this drawing with what the book is now using, this is now not a curve. Yeah, I can't write on that. So you got the picture here. Let me go through to write on it. This is now r of t. That's a vector, and so these should be vector brackets here. Okay? Let me picture something for you here. Here's your u vector, hk. Those are components of it. H in the x direction, k in the y direction. K slightly negative, x is fairly positive. Okay, that gives you a positive h in the minus k. Okay? So there's your vector, the vector u. It doesn't have to be a unit vector, so don't get that confused. Later we'll deal with them when they are, but this one doesn't have to be yet. Okay. Now, you want the vector r, this your pathway here, along which it's moving, in the direction of u, okay? And to figure out where this is, that would be the component of this, a, plus some parameter, t times h, comma, b, plus t times k, okay? Remember, k here happens to be negative, so that would actually be a negative number. But let the k carry the negative sign, don't worry about it, okay? So that is how you define this vector r. It has to have this. In other words, when t is equal to 0, you're at AB, right there. When t is negative, you're somewhere back here. When t is positive, you're somewhere out there. It just gives you that. It's how you represent a vector parallel to another vector, okay, through a given point. Okay, so the directional derivative, du alpha of AB, is the rate of change of alpha along the linear path through that point P, AB, in the direction of the vector u. So it's along there. What is the directional derivative along that? That's what we're talking about, okay? Now, you know this isn't going to be the maximum value it can have. That would be perpendicular here. You know, basically the shortest distance you get from this curve to that curve. This is not the shortest distance. This is the longer distance. This is not going to be your maximum or minimum vector. That would be the gradient vector. This is not. But this has to do with the gradient vector. Okay? Now, so that's the setup. All right. What this directional derivative is with respect to u at the point P, which is that notation we have right there, is defined to be this. All right, here it is. D sub u is a vector. The function f at AB, the path that we're taking, okay? Oh, that's through the point AB, sorry. That's, the whole thing gives you that path, okay? Here's what they tell you. This is equal to d by dt. Sorry about that, I've got hiccups. F of r of t. Now that's something we were just doing. The directional derivative is this thing that we just said, okay? And why in the world don't they mention that here? I don't know. What they get into is the definition of this, which is your limit, okay? And here's how they call it, and it is what it is, okay? That's the limit as t is approaching 0. Okay, as t is approaching 0, you're getting closer and closer to that point AB, right? T is approaching 0, you're closer and closer to that point AB. Yeah, is it that? Oh my goodness. Let's see, wait a minute. No. We started at 12:15 and we end at 1:55. He's trying to get out early today. Have you noticed that? I think he deserves to lose some class participation points, wouldn't you say? I'm just kidding. We don't have any class participation points. If I do, they're positive, not negative. Okay. All right. So rather than writing that down like we just had done it, they're giving it in terms of the limit. Okay, I know this was so exciting you hated to lose it, but here's what it is. The limit of f of a plus th. I couldn't remember which. Yeah, they did it that way too. I would have said ht, but they said th. B, I got a parentheses in there I don't need. Okay. Yeah. Pen. Okay, I couldn't remember. B plus TK, because that's your HK there. Okay. Minus F of AB, all divided by T. And that's a limit as T is going to 0. Okay? Which is, I mean, frankly, this is a function, okay? And this is basically definition, d by dt, the derivative of this function here, okay? And this is a two-dimensional thing. There's your components for your R of t, so that's exactly what it is. F of a plus th, comma b plus th, minus f of ab. So you're letting this get closer and closer here. That's why I said, this doesn't have to be a unit vector because it's shrinking down to a 0 vector. But the limit as that is approaching 0 of that difference over your t. All right. T minus 0 if you wanted to put that down there, but that doesn't make any sense. Yeah. Now, where they're heading with this is they're breaking that down into a component in the x direction, which would be in the I direction, the unit vector I direction. And then you'll do the same for unit vector j in the y direction, and that's all you have in this case. So basically, they just okay. Yeah, okay, here we go. I misread that and thought it was they came up with z, and I thought they shouldn't be doing that yet. F sub x at some point AB, at that point AB, is equal to the directional derivative in the I direction, and that is a unit vector there. Evaluate f of AB, and f sub y, the partial of the function f with respect to y, evaluated AB, would be the unit vector, the derivative with respect to j, the j component vector, unit vector, supposed to be a caret on top, okay, f of AB. Okay, and then you would have to proceed with that. Now, this is illustrating what I just had on the board a minute ago. I didn't think that they repeated it here, but they do. I should have known that. But, so the directional derivative in the direction of a unit vector, and they do call this a unit vector HK now. I don't think it has to be, but they're doing it as a unit vector, so let's leave it as a unit vector. Is a limit, if it exists, so directional derivative in the direction of the unit vector u of a function at some point p, that's the point AB. So here they wrote it as a function of point p, here they wrote it as a function of its components AB. Okay, is the limit as t approaches 0 of f of x a plus t h comma b plus th minus f of a b over t, and you could break that down in the partial of f with respect to x, in the I direction, partial of f with respect to y in the didn't do that, but you could have. We did that. Actually, they showed this. I should have gone this one first. Okay. Now, why? Okay. Sorry about that. This is going beyond. I thought, let me see if I can find this next figure. Yeah. Okay. Let's do this figure first, then we'll come back to that formula, because that goes a little beyond this. Okay. Now, okay. Directional derivative with respect to the unit vector u and the direction of unit vector u of the function evaluated at AB is the slope of the tangent line to the trace curve through that point Q, which they used to call P, but now they're calling Q. Yeah, there's a reason for that too. In the vertical plane P, through P, in the direction of U. Okay. So that's a lot of weasel words there. So basically what you have here is your point P, A, B. Now they're doing it in 3 dimensions here. We weren't in 3 dimensions before, we were only in 2. So they're extending this to 3 dimensions here. So the point AB0 would be in the XY plane at AB, but 0 on Z. If you go up to whatever the function value is there, alpha of AB, that'll be your Z value there, because that was the function that you were given. That identifies your point. Now this is now in 3 dimensions, which is fine. Come on, I'm about to sneeze. Okay. So that gives you on the surface up here at the point A on X, B on Y, and alpha of AB on Z. Okay? Draw a tangent line through that that's parallel to the direction, to the unit vector here. Here's the unit vector in the XY plane down here in this direction. Do that up here, only its projection in the XY plane is U, but up here it's very much different. Now that's way longer than it is. That projection would be probably somewhere down here. Okay? Okay, so that would be the projection of U up here along that line here. So frankly, it really seems like a weird way to express it. But that's your directional derivative. Is the slope of the tangent line to the trace curve through Q, okay, in the vertical plane that goes through P. So it has to be the plane that contains P and Q, because they have the same X and Y components. This one has a Z component, alpha of AB, but actually 0. This is your unit vector giving you the direction. So this would be the not unit vector up here, which would be the directional vector here, and that would give you the d sub u of this value would be this down here. The slope of the tangent line to that trace curve through that vertical plane that goes through P and Q in the direction of u. Okay? That defines what part of the plane you're dealing with. All right. Now with that done, to compute the directional derivative, we set r of t, okay, again doing that in 2 dimensions, then your directional derivative with respect to the unit vector in that direction, AB, is the derivative there, which is the of the composite function alpha of RT, and we can evaluate using the chain rule for paths. So let's go back to what we were doing before, okay? Doing all that stuff, and I except just to show that is these things, I don't know particularly why they went to the trouble of doing that. But now another way to express this is the gradient of f, as again is a vector, the gradient is a vector, evaluated at that point AB, okay, dotted with your r prime, and they say this now is at 0. Now, why have, oh wait, okay, sorry, I didn't read it enough. It said, to compute the directional derivative, we say r of t, blah, 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 then u of t is a derivative at time t equals 0 of the composite function f of r of t. So that would be, your t here is 0, okay. So you would use that in every respect here. And that is the same as the gradient of f evaluated at AB, the point AB, dotted with the unit vector u. And they do say that's a unit vector now, so I'll put a hat over it. What they're saying is r of t, that's not how I wanted to express that. Okay. R of t, the r prime at t equals 0, time t equals 0, is that unit vector in the u direction. Okay. Which is exactly the same formula we had before, used in the same way. And in 3 dimensions then, if we were dealing in 3 dimensions, your directional derivative with respect to the unit vector u, I probably should make that a unit vector now because they're saying it is. Just in my gut, I don't feel like it's got to be, but we'll put it that way just in case. Of u in 3 dimensions, f of a, b, c is going to be del f, and that's going to be your gradient at f at the point a, b, c, dotted with your r prime at 0, which is the same as dotted with the u vector. Oops, unit vector. Since they're saying it needs to be a unit vector, let's keep it that way. Okay, start over. Okay. Now, that then leads to this formula. Okay. Now, I don't know, this is from the last edition, why they suddenly changed from being U to V, okay? Just make sure that doesn't contradict something else we had. No, I don't believe so. All right. Now, here again, that V may be a unit vector, but I see no reason that it has to be. Okay? But let it go with that. And that's the general definition. This is in 2 dimensions. To make it 3 dimensions, just do ABC by F up there and down there. And then, of course, your V will have 3 components as well. Okay. So let's get ready for example 6. Let me just make sure there's nothing else there. Okay. I don't see anything like that slide, so let's go back and do it here. Example 6. Let f of xy equal to x e to the y. the point that you're dealing with, P, is the point 2, -1. Okay. Okay. And, okay. I've been saying all along, this vector V is not a unit vector. It doesn't have to be. The vector V is 2, I say 2 and write 3. Where is, I don't know what's going on. Okay, 2, 3. I think I was reading faster than I was writing. Okay, and obviously that is not a unit vector. Okay? And it says calculate the directional derivative in the direction of the vector V. Okay? And the first thing they say, note that V is not a unit vector. We just did. So we replace it with the unit vector U. This is a unit vector, and it needs to be in the direction of V. So does anyone remember how to get that? What would be the unit vector U in the direction of V? Yeah, divide by the magnitude. Okay, and what's the magnitude?
I'll just have to say it out loud. So I don't want to.
What's that?
It is 2 squared plus 3.
Yes, 2 squared plus 3 squared. Square root of that, which would be the square root of? Second? 4 plus 9, which is 13. Square root of 13. So what would be your unit vector in that direction?
It would be 2 divided by
Square root of 13, comma,
and then
3 divided by the square root of 13. Okay, that's the unit vector. Now, if you don't believe me that is a unit vector, then do the same thing. Find the magnitude of this. That would be 4 over 13 plus 9 over 13, right? That would be 13 over 13. Yep, its magnitude would be 1. So, yeah, that is the unit vector in the same direction as the vector V. All right. So, we've got the unit vector. To compute the gradient at P, and here's your P, okay, what we'll do is the gradient of F, remembering this is now a vector, and what would it be?
it would just be e to the y.
Yeah, e to the y is the x component.
Yeah, and the y component would just be x e to the y.
X e to the y is the y component. Okay. Now we want it at the point 2, -1, right? Did I write it right? Yeah, 2, -1. So the gradient vector F at 2, -1 would be
E to the, well, that's supposed to be,
second,
okay, e to the -1.
e to the -1,
And,
comma,
2 times e to the -1.
yeah, 2e to the -1. Tell you what, this air that's coming out of here is extraordinarily dry. I mean, it's fairly warm, but it's very dry. My whole head is, feels like it's no moisture in there at all. Okay. So there is your gradient vector at the values 2, 1. Okay? Now, what do we do with that?
I believe we multiply it.
Okay. Yeah. Now, here's sort of an issue that we have here. We're computing that directional derivative. And if you remember, let's see if I can find it. Yeah, well, here it is right here, right there. There is your gradient at this. We're going to dot that with the v vector, not with the u vector, with the v vector, okay? And that's going to be 2, 3. So I'm trying to figure out why in the world they had us calculate the u vector. Well, I'll take something back. I'm jumping back and forth between two notations. That's the old and the new. In the old notation, v was also a unit vector. So what we do is not with respect to v, but with respect to u. Okay? So, simple change here. Our unit vector is, unit vector is 2 over root 13. 3 over root 13. Okay. So dot those two together. And this will give you the dot u. Okay. And this will give you directional derivative in direction of u at the point f of AB. Okay. What will that be? Yeah, you will need to put it in a calculator. Let me write it down first. It's 2 root 13 e to the minus 1, comma, 6. Over root 13 e to the minus 1. Okay, I'm sorry. It's not a comma, it's a plus. You're adding those two together. Okay? So when you add those together, that gives you 8 over root 13 e. Okay? Now that e is not inside the radical. Okay? So
well, leave it in that form.
Well, let's see what they do. They put AE to the minus 1, which we had, but I thought it would be better down there. So let's do it in decimal form. 8 divided by square root of 13 and divide that by that answer by E. Doesn't matter how you do it. You could leave it 8e to the minus 1. You could calculate that first, divided by root 13. What do you get? 0.8 what? 1.6. They round to 8.2. Okay. Good. So, here's what they're saying. Picture this, imagine this, think of it as a function is representing a mountain, some shape here. That's your function, f, okay, x e to the y, whatever it is, okay? You're traveling on that mountain in a certain direction. That's your x. Your v. Get that to a unit vector, because v doesn't have to be a unit vector. Get it to a unit vector, and then do that directional derivative of that, which is simply what we did before. Your gradient f dotted with the unit vector u. Make sure it's the unit vector, not in this representation, v is the unit vector. In our representation, v was not a unit vector. Okay. You get it in that form, and then do the dot product. Okay.
So, what did we just calculate again? The dv of AB, what is that again?
Okay. This slide was from the old edition, and for some reason they changed the unit vector from calling it u to v. Okay, that was what we got in the last the directional derivative, and that's this v here is a unit vector. But in the new book, they had v not being a unit vector, so you have to get it in terms of the unit vector and then do the thing, and that gives you the answer. Okay? So this representation here, v is a unit vector. In our problem, v was not a unit vector, so you get it to the unit vector and then do it with respect to that. Okay. That's one problem with using two different notations here, or two different additions. So let's move on to example 7, which we don't have a slide for either, I'm pretty sure. So let's clear this. I hit the wrong key again. Yeah, I don't know. I guess what I did is hit the wrong button, because I put it right on there, but never mind. Okay. It's confusing me today. Here's example 7. Find the rate of change of pressure at the point Q, and Q is the point 121. No, sorry. Q is a point, so you don't use vector brackets, you use parentheses. 1, 2, 1. That's a point. 1, 2, 1. In the direction of V, and V is a direction vector, and that is 0, 1, 1. And these are angle brackets. And I swear, it gets me so, just glancing at this in the book, it's hard to see whether that's a parentheses or that, because they make a real wide angle bracket. I like to make them really angular so you know that's a vector. Okay. Now, obviously, that's not a unit vector, right? Okay. Okay. Assuming that the pressure in millibars is given by, here's your function, F, and this is your pressure. I wish they hadn't called it F. F at X, Y, Z is equal to 1,000. That gets you up to sea level in millibars, plus 0.01 okay, YZ squared plus X squared Z, I keep losing my place here, minus XY squared. No. No, 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 no. Just keep wanting to put angle brackets in where they don't belong. Okay, there's a scalar function. No brackets in it, angle brackets. Okay. And X, Y, and Z are in kilometers. Okay. Whew. So you got change of depression at millibars, and your length measurements are kilometers, so they weigh thousandths of a bar, 1,000 meters. Yeah, rather strange. So what we want to do is find the gradient of this function at that point. Okay, so that's where we'll start. Gradient of F. It's going to be a vector, and what will it be? And yeah, well, let's just first do it X, Y, Z, okay? Okay, don't plug in yet. Take the gradient first. Oh, maybe that's what you're doing. What were you saying? Okay, what were you saying?
I was just saying 0, 0, and then 2x.
Okay. Where are you getting 0, 0?
Oh, the function of x, y, and z, 1,000 plus 0.01.
Yeah.
And then y, I got a 0 from the 1,000.
Oh, got it. Okay, got it. Okay. Okay.
So I got 0, and then 0 for the y, z squared, whatever.
All right.
And then the next is going to be 2x to the z.
Okay. 0.01 times 2xz, right?
Yeah. Oh, my bad. 0.01.
Right.
And oh yeah, and negative y squared.
Negative y squared. That's your x component of your gradient vector. Okay, that's the partial of the function with respect to x. Okay, how about your y?
0. Can I just go ahead and go straight to the point where it has the y in it? I don't got it.
Okay, well, that will need to be there at some point, but okay, go for it.
Alright, z squared
Z squared
minus x squared.
not 2xy,
Oh, yeah, 2x squared, I'm sorry.
2xy.
Yeah. Bad.
Okay, that's your y component. Z component,
0.01 2y. Yeah, 2yz. Okay. And plus x squared.
done. Okay. Now to get that at the point 1, 2, 1, the gradient of f at 1, 2, 1. Now we plug in. Okay. Okay. Whoa! Almost, isn't it? Yeah. Okay. That will be, let's first plug in the 1, 2, 1 here. That will be 2 times 1 times 1. So that would be 2 minus 4. So that will be a negative 2 times that. So negative 0.02. By it? Okay. Comma. And when you plug in 1, 2, 1 there, that would be 1 squared minus 2 times 1 times 2. So that would be 3. And that would be a negative there too. Negative 0.03. I think. You check me. Okay. The third point is 2 times 2, 4 times 1. That would be 4 plus 1, 5, 0.05. Okay, there's the gradient of that function at the point 1, 2, 1. You buy it?
Yeah.
Okay. Now, next thing we've got to do, we need to get the u vector, okay, the unit vector. What will it be?
Square root of 2.
Okay, yeah, divided by the square root of 2, so it's 1 over root 2, 0, 1 over root 2, 1 over root 2. Okay, that's your u vector, okay? Now, what are we looking for? I think it is, find the unit vector. Wait, I'm in the wrong problem, okay. Where is my problem? Oh, it's up here, okay. Find the rate of change of pressure, okay, assuming, okay, so this will be change of, okay, it'll be millibars per kilometer is basically what we're dealing with here, okay. Let's see, just to catch, yeah, they got it right, and we got that right. So your directional derivative, okay, I'm going to, okay, what were they asking for? The rate of change of pressure per unit kilometer, I guess. So that's d by dt, that's a rate of F, okay, of V, okay, Yeah, I think that's how you express it. And that, by definition, is, let me go back and make sure. Yeah, that's all they had to do. They put a T in there. I knew they had something else written there. Yeah, okay. And this is directional derivative in direction of the unit vector u with f of the function f at 1, 2, 1. Okay? And that's defined to be the gradient of f at 1, 2, 1, dotted with the u vector, the unit vector. Okay? So this will be negative 0.02, negative 0.03, 0.05, dotted with, that's supposed to be an angle bracket, 0, 1 over root 2, comma, 1 over root 2. Okay? And let's do that dot product. Zero, got it? Huh? Negative 0.03 over root 2.
Okay.
Plus
0.05.
0.05 over root 2. And that would be 0.02 over root 2. And if you'll punch that in your calculator, see what you get.
I got 0.014.
That's it, 0.014. Units are millibars per kilometer. Okay, strange units, but that's what we got, millibars per kilometer. All right, that ends what we have time for today. In fact, we went a little over. Sorry about that. No extra charge, though. And we'll pick up next time with properties of the gradient. We'll pick up and go from there. Let me give you a few homework exercises here. This is a long section. Do any of the odds, any of the odds, either 1 or 3 or both, either 5 or 7 or both, any of the odds 9 through 19, any of the odds 21 to 29, and any either 31 or 33 or both. I think we'll stop there and pick up the rest of those later. All right. Good deal.
Have you got another piece?